Matrices function as structural maps. When we look at an array of numbers, we are observing the encoded geometry of a vector space. The challenge lies in using these grids to reveal that hidden architecture. This starts with the concept of a subspace. A subset of a vector space qualifies as a subspace only if it remains closed. Adding any two internal vectors, or scaling one by a constant, must result in a vector that stays within that same set. If we take a finite set of vectors and calculate every possible linear combination, stretching, flipping, and adding them, we generate an infinite set. This expanse is the span. To bridge abstract geometry with rigorous computation, we rely on the framework established in Hoffman and Kunze's linear algebra. Consider the central tension of this field. If you are handed two entirely different sets of vectors, how do you prove they generate the exact same infinite subspace? You cannot test infinity vector by vector. Instead, we use the matrix to calculate the specific, irreducible properties of that infinite span. We manipulate these matrices using three elementary row operations: scaling a row, adding a multiple of one row to another, and swapping rows. When we place coordinate vectors into the rows of a matrix, each row represents a physical vector sitting within our subspace. Performing a row operation is algebraically identical to calculating a new linear combination of those original vectors. You are scaling and merging them in real time. Because row operations are strictly linear combinations, the new vectors they produce are bound by the same geometric constraints. They cannot break out of the original span. Row operations might scramble the individual vectors, but they leave the overarching geometric room, the subspace, entirely intact. This leads to the definition of row equivalence. Two matrices are row equivalent if one can be transformed into the other through a finite sequence of these operations. Hoffman and Kunze formalized the connection between algebra and geometry in Theorem 9. Theorem 9 proves that row-equivalent matrices are guaranteed to have the exact same row space. If matrix A can be reduced to matrix B, their spans are identical. Sharing a row space is a start, but we need a standardized method to compare any two sets of vectors without relying on trial and error. To make matrices a viable diagnostic tool, we must identify a universal, irreducible simplest form for any subspace. That simplest form is the row-reduced echelon form, or RREF. The RREF is defined by a descending staircase of leading ones, called pivots. Every pivot zeroes out everything above and below it. According to Theorem 10, these non-zero rows form a mathematically perfect basis for its row space. Theorem 11 then provides the final proof. Every single subspace is associated with exactly one unique row-reduced echelon matrix. For students tackling competitive exams, the strategy is direct. To see if two sets of vectors span the same space, row-reduce both. If the final RREFs match exactly, the spaces are identical. The row-reduced echelon form acts as an unforgeable identifier. It reveals the exact, unique basis for the space it describes. We can apply these theorems to the concrete computations found in section 2.6. We need to answer three questions. Are these vectors linearly independent? Does an arbitrary vector lie in their span? And how do we describe the subspace's constraints? We'll use the data from example 21, a set of three vectors in a four-dimensional space. Stacking them horizontally gives us our 3x4 matrix A. We must now subject matrix A to row reduction to uncover its structural truth. While matrix A represents the messy, raw data, the reduction process acts as a filter to distill that data into its pure basis. Finding the final RREF, matrix R, is only half the work. We also need an algebraic record of how we combined those original vectors. We use the augmented matrix technique, where we append an identity matrix to our starting data to track our progress. Applying operations across the entire block transforms the left side into our RREF. Simultaneously, the identity matrix mutates into a tracking matrix, matrix P. This establishes the relationship R equals P times A. Matrix P acts as a translation dictionary between the original vectors and the RREF basis. In example 21, our three starting vectors yielded exactly three non-zero rows in matrix R. Since no rows were eliminated during reduction, the original vectors were linearly independent, defining a three-dimensional subspace. Matrix P provides the explicit path between the messy original vectors and the pristine RREF basis. It records every transformation, allowing us to reconstruct the exact relationship between the two. This toolkit can be extended to find the sum of two distinct subspaces, W1 and W2. To find the sum, we stack the basis vectors of W1 and W2 together to form a single, larger matrix. Row-reducing this combined matrix reveals the surviving non-zero rows, which form the basis for the combined space W1 plus W2. Finding the intersection of W1 and W2 is a more complex calculation. Finding the intersection requires identifying where a linear combination from W1 equals a linear combination from W2. We solve this by setting up homogeneous systems. The solutions to this system define the exact coordinate constraints of the overlapping intersection. Whether merging spaces or finding their core, the RREF algorithm remains the universal mathematical engine for the solution. Linear algebra is a constant negotiation between geometry and algebra. In the realm of geometry, subspaces are rigid, infinite planes or lines securely anchored to the central origin point. Algebraically, row reduction is the act of straightening and rotating those planes until their coordinate systems align with our standard axes. Row-equivalence ensures that while the algebra shifts, the underlying geometry of the space remains absolute. For students tackling exams like the CSIR NET, this duality transforms abstract theory into a repeatable computational strategy for the most dense linear algebra problems. If this clarified your understanding of vector spaces, like the video and subscribe. Let me know below which textbook topic we should tackle next. A text like Hoffman and Kunze functions as a toolkit for structural thinking. Every theorem is a precise instrument for decoding the architecture of mathematics.